Yep. So just a quick about. So I work for NCC Group in a team of 3 people, just called the Exploit Development Group. And we basically just mostly focus on end days until recently we started doing some Pwn2Own stuff. So we joined the Pwn2Own Austin 2021, which is more like IoT and embedded stuff. And we exploited NAS and Lexmark printer and released some blogs talking about the bugs we exploited in methodology and stuff, if you're interested. So yeah, basically we ended up wanting to, or tried to compete in Pwn2Own Desktop 2022, but it didn't quite go as planned. So basically, at first we found a bug and exploited it, and we were happy and we were all ready to go. And then it was patched before the competition, so we had to start from scratch, which was kind of too bad. So we found a second vulnerability, and we were pretty well on our way to exploiting it. It definitely was exploitable. And then that was also publicly patched before we were finished, so we had to start from scratch again, but it was getting kind of late. And unfortunately, we didn't finish exploiting the third bug in time, but it was still interesting experience. And we decided to disclose it rather than sit on it for a year, just because probably it would get found anyways. And yeah, so basically this talk is just about the third bug, because in the end there was no like collisions for this bug at Pwn2Own or anything, so it's kind of interesting. And yeah, so at the time of the competition, the target was Ubuntu 22.04, and it was kernel 5.15. So yeah, I guess I'm kind of fortunate to follow Sam's presentation in that I'm not going to talk too much about the methodology and stuff. It's just going to mostly be a big technical dump of the bug and how we exploited it, but just we mostly followed the typical tooling stuff that you do for Linux kernel debugging and whatnot. I guess the one thing that's worth noting that I've noticed some people don't seem to know about is that the Linux kernel sources include some helper Python scripts that you can import into GDB that actually let you analyze a bunch of the structures. So like if you have a breakpoint and you want to only trigger the breakpoint if the user land process is a specific one, they basically provide you structures for that version that let you do that check inside of GDB, which is really nice. But otherwise, it's just pretty typical stuff. PA hole for structure analysis. We did end up using CodeQL for some querying structure sizes and members and stuff, which I'll talk about. And then I guess the other big thing was we did a lot of like slab cache analysis during the research. And at first we were using ftrace, which a lot of people seem to be using, but we found that just the information it provides in the level of analysis it let us do wasn't quite what we wanted, because we're used to using some other tools that we had written in userland. So anyways, we ended up writing our own tool based off some other open source tool called slab DBG that just works on the latest kernels and stuff, and it's much nicer for analyzing all sorts of stuff in the slab allocator. So we're going to release that open source eventually, but it's not quite open source yet. But stay tuned for that, I guess. So yeah, I'm basically just going to go over like the netlink, netfilter, and nftables parts of the Linux kernel, just like a whirlwind up to the point of like knowing enough to understand the bug, and then we'll just talk about how to exploit it and then look at how they patched it. So yeah, basically, most people that use Linux are probably familiar with this userland utility called NFT, which is used for configuring the firewall. And basically, like, if you want to add a rule for something like dropping a TCP port 80, you just run a command like this, and it's really well documented and fairly easy to use compared to the tools in the old days. But we're interested in, like, how does this work underneath? Because parsing, like, the logic of these types of rules and building structures based on them and stuff is quite complicated. So basically, everything is built around netlink, which maybe people are familiar with, but basically you can just create a socket and then you can send packets to that socket to talk to various parts of the Linux kernel, like networking subsystem. And there's a really nice userland library for helping you build the packets, because it's kind of annoying to do by hand. And then net filter is just basically like a bunch of kind of hooks into different parts of the Linux networking subsystem. So things like network address translation and what we're interested in, the firewall stuff. And basically you can just create packets that talk to these different hooked portions of the kernel. And then finally, again, what we're interested in is nftables kernel module. And yeah, basically it's like the new as in like 10 years or something, firewall in the Linux kernel. And it replaced IP tables. And again, there's a pretty nice userland library for constructing the packets and stuff, because it's also quite annoying to do by hand if you have to tweak anything. And most importantly, access to stuff like netfilter and nftables is based on whether or not you have the netadmin capability. And I'm sure a lot of people are aware on Ubuntu, you can enter namespaces as an unprivileged user. So you can enter a network namespace and basically obtain this capability and then expose the functionality that you want to target. So yeah, recently this like nftables module has been pretty popular, just especially this year. I think we started fuzzing it specifically around when David Bowman released his blog. And if you're interested in any of the nftables internals and stuff and follow up on like what I present here, definitely read David Bowman's blog, because it goes into the most detail just about netlink and nftables packets and all that kind of stuff. But it's all pretty interesting reads if you want to go deeper. And interestingly, at least one team, Team Orca, of C Security, which I think is from Singapore, they ended up exploiting a bug in the same component successfully at Pwn2Own. So that's kind of cool. And I'm sure there'll be more in the future. So yeah, basically I'm going to have to explain a whole bunch of structures that are used internally so that we can understand the bug. So basically everything is grouped into tables, which people that have, again, used NFT will be a bit familiar with. But basically a table is just a group of chains, and they're typically associated with like a specific networking protocol. So like IPv4 will have a whole bunch of chains associated with it. And then the chains typically just have like a default policy of accept or drop. And then the chains themselves hold a group of rules, which, explains how to actually process the packets themselves. And basically the rules are just made up of a group of expressions, which are more discrete pieces of like logic for processing the actual packets themselves. And there's a ton of different expressions. Again, the blog by David Bowman goes over a lot of different ones. There's too many to cover. But really, we're just interested in these three that we use during exploitation. And I'll go into them in more detail in a second. And then there's the concept of sets. And so basically the idea is like if you create a rule that is going to blacklist a list of IPs, or has a list of ports or whatever. Basically, those sets of like numbers are represented in the kernel in just like a data structure, and they call it a set, so NFT set structure. And basically, yeah, the elements inside of the data structure are just referred to as elements, which I'll mention a couple times. And given the name of the talk, we're specifically interested in this set structure. And it's quite a big structure. There's a lot of different fields, too many to go over, but these are the ones we're mostly interested in, and I'll go into some detail about them. So there's a member called list, which is basically just a doubly linked list of sets that are associated with a table. So if you have multiple like rules referencing different sets of data, they'll all just be linked on this same doubly linked list associated with whatever table they're part of. There's also a doubly linked list called bindings, and basically if you have some expression that's referencing some element in the set, it gets bound to the set, and it by being bound, it basically means it gets added to this doubly linked list. When you're interacting with a set through an expression or whatever, you need to look it up somehow. So there's a name, which is important if you end up corrupting things later. There's like a reference counter. And when you're creating this set in the first place, so you're building this netlink packet that, is talking to NF tables and say, okay, I want to build this set. They give you the ability to add some arbitrary data that you can store inline inside of the structure that ends up going on this, the slab cache. And you can also read this data out from the set after the fact, which will be from userland, which will be useful later. And so then there's a length field that says how much data did you actually store there. And then interestingly, there's a function table pointer for doing operations on the set, like adding, deleting elements and stuff like that. And so by default, again, it's a fairly big structure. So by default, it's stored on the 512 byte slab cache. But because of the variable length user data you can supply, you can get it onto the 1024 byte slab cache, which is useful. So we want to take a bit of a closer look at the bindings member specifically. So when an expression references the set, it gets bound to the set. And so basically any expression that's capable of referencing a set will embed this NFT set binding structure. And it basically just has the list member, and that's what ends up being put onto the bindings list. And so the entries on each list point to that list member of this structure rather than the beginning of the expression itself, which is kind of important. And so then expressions themselves, basically there's like a more generic structure called NFT_expression. And basically every type of expression in the kernel extends from this. So they just has like its own little function pointer member and then an inline array that's going to contain the actual specific expression type. So like at the bottom, you can see we're going to create we want to reference an NFT lookup expression. And so it calls this function to just pull out the data member of that more generic structure. And this is only just noteworthy because if you're sort of analyzing the structures in the kernel and you want to know what slab cache a structure is allocated on, if you don't include the size of the NFT expression structure in that calculation, you'll be wrong and you'll be looking at the wrong cache. So it's worth knowing. So yeah, the expressions we're interested in, the lookup one, basically, the idea is that it just fetches some value from a set, and it's a 48 byte structure, so, allocated on that slab cache. And we're mostly just interested in the fact that the binding structure entry is the last, entry in the structure. We don't really care what else it's used for. And similarly, the dynamic set expression, we don't care too much about anything that it's used for, except that it can reference a set. Again, the binding structure is at the bottom of the structure, and this one's a bit bigger, 96 byte slab cache. So the way this would normally look is you've got some set, and then you've got, you send some expressions over netlink, and they reference the set, so they just get added to the bindings list. And going back to the beginning, I mentioned there's the list, doubly linked list as well. So in this case, okay, there's a table and there's multiple sets associated with this table, and each one happens to have expressions linked on to the bindings list. So that's just like a high level overview of what you can think about it in your head. So there's another sort of important bit, which is like when you're creating the set originally, you send the packet over netlink, you can basically say that you want to embed certain expressions inside of the set itself. And this is a little bit different because I said expressions are normally used to process the actual packets that are coming in over the network. But in this case, the expressions are meant to get run when data in the set is being updated. But there's only a limited number of types of expressions that can actually be embedded in a set, and they're called stateful expressions. Which will be important. So that's basically like a quick whirlwind of like the structures involved in how to, at least enough to understand the bug. So, we basically were fuzzing. I think after we read David Bowman's blog, we decided to spin up like a syscall fuzzer specifically targeting NF tables just because it seemed like a fruitful area. And this bug was specifically compelling because syscaller wasn't able to automatically generate a repro file, because normally it'll give you like some C that you can run to trigger it. And in this case, it couldn't. And because we already got burnt twice with bugs, we figured this might mean that other people didn't want to look at this bug if other people had already fuzzed it. So we decided to do that. And basically it's a use after free while handling expressions on the bindings list that I just explained. And it's quite limited insofar as we'll see, you can basically just write one pointer that you don't control to an uncontrolled offset somewhere. And after we disclosed it and stuff, and it was patched, someone else noticed, interestingly, that Google's fuzzing infrastructure had actually found it already in November 2021, which we didn't know about, and it was automatically closed as invalid, which I actually have no idea why. Maybe because there's no repro, so it figured it wasn't real. But yeah, so basically I mentioned that when you're allocating a set, you can embed certain expressions inside, and those expressions can only be of a certain type. Otherwise the set is considered invalid. And so this is the function responsible for that. And interestingly, we can see what it does. At the top, it calls NFT expression initialize, and that will actually allocate the expression structure like on the slab cache and call an initialization routine. And only after it does all that, it checks the flag to see, is this expression legit or not, like for being embedded in a set. And if not, it just destroys it immediately. And so this is actually kind of interesting because if there's any desynchronization between the initialization routine and the destruction routine, because it's not maybe normally called in this type of context, there could be some interesting bugs. So we need to look a little bit closer at what happens. So the destruction routine itself, basically, the only thing that's important is at the bottom, it just ends up calling into the destruction routine associated with the given expression that's being destroyed. And then at the top, like after it calls that helper function, it just frees the expression, and that's all it does. So we need to look specifically at the expressions destroy routines. And yeah, so these two expressions I mentioned, when they get initialized, they end up getting bound to the set that they reference. So they call the NF tables bind set. But neither of their destruction routines actually removes themselves from the bindings list itself. The normal context in which they get called, they get unbound first and then destroyed. So this leads to a use after free because they get destroyed and there's still linkage on the bindings list pointing to them. And that means that any update to the linked list after the fact will potentially write to a free chunk or something that's been replaced, which means that we can either write the address of a set or one of the expressions into freed memory or whatever replaces it. So this is just an example of like the dynamic set initialization routine. We can see that it calls the function that's binding it to the set bindings doubly linked list. The other stuff doesn't really matter. We just know it's on the list that we're interested in. And then the destruction routine is a little bit more complicated, but you can just basically avoid calling the first for loops function entirely, and then it just ends up calling this NF tables destroy set, which tries to destroy the set itself, but only if the set bindings list is empty, and it's not empty because the expression just got added to it, so basically it doesn't call it. And so effectively the destruction routine does nothing in this particular case. So it just frees the expression and leaves the entry on the bindings list. So yeah, if we want to like walk through the steps of how we would, for instance, write the address of a set to a free chunk, basically you need to create some valid set that expressions can reference during the initialization so that there's a bindings list that exists for them to get added to. And then basically we create the expression to bind it to that set, which gets added to the list. And then we create a new invalid set. And that invalid set will embed one of these buggy expressions. And so the buggy expression gets added to the bindings list, and then the code will say, oh, it's not stateful, and then it gets destroyed. And then oh, actually, there's one I forgot to mention when I said the second point. There's an important point. When you create the valid set, or initially, if you want to be able to write the address of the set into the free chunk, you have to first bind some legitimate expression to the set so that there's a pre-existing entry on the bindings list. And then when you create the invalid set, the new expression gets added after that valid expression entry on the linked list. And then it gets freed. So you've got a dangling pointer. And then what you do is you destroy the good expression on the list, which updates the linkage. And so basically it'll write the address of set bindings into the free pointer or the free chunk. But I know that that's kind of hard to understand, so I'll go over it visually because it'll be a bit easier. So in this case on the left, we've got a valid set that we're going to get expressions to reference. And then we've added some legitimate expression that's just on the bindings list. And then on the right, we've got some invalid set that we're creating, and embedded inside of it is this dynamic set expression, which is not an okay expression to have. But we can see at this stage, it's already been bound to the bindings linked list. So then the set is deemed invalid. So the dynamic set expression gets freed. And so now the valid expression has a dangling pointer. And now what we do is we free the valid expression, and so then it updates the prev pointer of the free chunk to point backwards into set bindings, which is our use after free. And that's basically it. So it's fairly limited insofar as what you can write, and it doesn't give too many options to how to exploit it. Like some ideas. Because we can write a pointer, it would kind of be nice to be able to overwrite some length parameter. So like replace the free chunk with some other structure value that happens to have an overlapping length that maybe gives you an out of bounds read or write. That would be like ideal, but we didn't find something like that. Another idea is to overwrite some pointer in a structure with the new pointer that points to set or points to another expression, and maybe let us build a better use after free primitive. And then the other obvious thing would just be to write the pointer into some buffer that we can leak back to userland to at least get a limited memory revelation. So the first thing we did, just for an easy win and just to help build the memory model, because when you're doing this stuff, it can be confusing. So it's nice to have anything that works. We decided to just leak the address of a set or expression into userland. So how do we leak the data? So there's a pretty popular technique that people have used in the past for Linux kernel, stuff like this. Basically, the Linux kernel includes like this key rendering service where you can just build keys and add them into the kernel. And you can basically add your own arbitrary data into these keys, which get allocated using this user key payload structure. And because the size that you provide is variable, you can kind of control which slab cache it gets allocated on. And then you can read the data back out, the payload data that you provided, you can read it back out into userland after the fact, just using this key cuddle syscall. So when we trigger this bug using the key stuff, I'll refer to it as use after free 1, and the set that we're going to abuse is called set1. So again, exactly the same as before. We've got set1, which is the thing that our expressions can reference, the legit expression, and then we're going to use our use after free dynamic set. So we trigger the state where it's dangling on the bindings list, and then we replace it with user key payload, and then we unlink the legit expression, and it writes the address of set1 bindings into the user key payload. And then from userland, we can leak the address of set1 bindings, which is nice. But it's not that nice. I mean, what do you do with like some random slab cache address? Not much. But it's a good start because you learn how to exploit the bug a little bit and stuff and build up the methodology for doing something a little bit more difficult. So the next step is to try to free some other object in the kernel. So basically the goal here is we want to find some object that lives on the 48 or 96 byte slab cache so that we can replace the lookup or dynamic set structure. And we want whatever object we find that can live there to have pointer member that happens to overlap with the offset that we can write during the use after free write. But the main constraint here is that not only does there have to be an overlapping pointer, but it's got to be one that when we destroy whatever the object that we're writing to, it will also try to free that pointer. And that way we can build like an actual free primitive, so we can free something else. So basically there's two options here. Because the pointer you write, points to the bindings member itself, and not the beginning of the expression, or the set, it's a little bit quirky. So what happens is when you free it, you're freeing like at a misaligned address inside of the expression or set. And so the free will start there and it will overlap into the adjacent object. And in the case of the expression, because the bindings member is the last member of the structure, it's actually kind of quirky and potentially unreliable. And I don't go into too many details why we didn't use it. We'll release a blog with details about why. But in the case of set, the bindings member is just the second member. So you're basically you can free all of the set from the second member onwards, and you don't have to rely on any adjacent object being there on the same slab cache, so it's more reliable. Yep. So the question is, okay, so how do we find like a structure that actually meets these requirements? So we use CodeQL. So basically we just wrote this CodeQL query, and basically you can just use queries like this to find stuff inside the Linux kernel matching a set of rules. And basically we just say, okay, find us some structure that's allocated from one of the heap functions that we're interested in that happens to be of size like 96 bytes. So it's on the right slab cache. And the offsets the members at specific offsets are referenced as pointers. So it meets our constraints. And then basically this spits out a list of candidate structures that you still have to go through manually. And then you're looking for you're still looking to see, okay, this structure seems to maybe match. Can I allocate this structure from userland? Because if not, then you can't use it for like the attack. And then also, is the overlapping member actually freeable on demand? And believe it or not, we did find one. So there's this C group FS context structure, which is 96 bytes, so it's on the right slab cache. And basically there's a member called release agent that happens to perfectly overlap with the prev pointer of the bindings doubly linked list entry. And you can just allocate them from userland by calling this fs open syscall. And then when you close the file descriptor associated with it, it will just free that structure, and it happens to also free the release agent pointer. So this is just what the structure looks like. You can see there's a name and release agent members, and both of those actually overlap with next and prev, so we could use either one. And then this is the destruction routine. So when you're closing the C group, this ends up getting called, and we can see it calls kfree on both the name and release agent member, and then it finally frees the actual structure itself. So this is exactly what we wanted, and fortunately, the members line up okay. So we found a candidate structure, but we have to actually create the primitive first to abuse it. So this setting up the primitive, I refer to as use after free 2, and we'll use a different set for it. So again, same as before, we've got now set 2, legitimate expression, and some use after free dynamic set. We free it to trigger the dangling pointer scenario. This time we replace the free chunk with C group FS context. Then we unlink the expression, and now we've got a release agent member pointing back into set 2 at the location of bindings. And that's basically it. Like, that's our new free primitive. It lets us free set 2. And so in order to be able to free set 2, we refer to it as use after free 3, because you can still operate on the set after it's been freed, because you still have a reference to it. And so we're going to replace set 2, and what we replace there, we refer to it as fake set 1. So this is our free primitive that lets us free set2. Basically, all we have to do is close this C group, which will free the C group FS context structure. And then basically what happens is everything after the list member of set2 is freed. So we can replace it with something else that we want. And in this case, we use the Fuse userland driver and a syscall called setxadder. And this is a really popular technique lately. But basically the idea is you can create some file in userland and cause, when you call like setxadder, you can supply a path. And in the process of trying to access that path, it goes up through the kernel and back into userland in a Fuse driver that you basically control. So you can basically pause the kernel while it's copying data into a chunk, and it allows you to just replace some chunk with effectively arbitrary data at an almost arbitrary size. So it's easy to create a chunk of the size that we need at like NFT set and just replace it all with completely controlled values. So from here, what we want to do is get some sort of memory revelation, because eventually we're going to want to bypass KSLR and stuff. And so if you think back to the first use after free we did, we leaked some address on the slab cache, which at the time didn't seem that useful, but now it's useful because maybe we can use that as a memory revelation. So when we replace set2 with the fake set, we basically can set the UData member to the address that we leaked from the slab cache of set1. We can set the length to the size of the set1 structure. And there's one constraint, which is that the name has to be valid, and we end up clobbering it. But you can, since we know the address of set1 already, when we create set1 initially, we can just pre-populate part of the user data with some fake name that we'll use after the fact. And then when we continue to we access set2 and fake set via netlink, we have some legitimate way of looking up the set after the fact. So this lets us leak the contents of set1 back into userland, which is nice. It leaks us the NF tables kernel module data pointer because of the function pointer table. But unfortunately, that is fairly limited for ROP gadgets, so it's not actually as useful as we wanted. But basically, this is what it looks like. So when we create the fake set and we've replaced set2, the name just points to some pre-existing value that we had populated in set1 during creation. UData points to the beginning of the set. We've got the length that encapsulates the full set. And then that gives us like a limited leak, at least of nftables.ko. But we can do better than that, because we want ideally a full KSLR bypass, so get the address of VM Linux. So if you recall way back, I said that there's the linked list of all the sets associated with a table. So when we create the sets, we can basically put them on the same table. And so when we leak set1, we can have the next pointer of the list member actually pointing back to the fake set. So we can leak the address of the fake set as well, which will be useful in the future because then we know where data is we fully control a little bit later. And then on the previous slide, I had said, well, we can set UDLEN to the size of set1. Well, actually, it's not limited to that size. So we can leak objects adjacent to set1 as well. So basically, what we found a good candidate was these TTY structures that live on the 1024 byte slab cache. And basically, you just open this pseudo terminal path, and every time you open one, it allocates one of these structures on the slab cache. So basically, you can just spray a whole bunch of these structures, then allocate set1, and be reasonably sure that there's a TDY structure adjacent to it. And even if there's not, you can start from scratch. The one exception to it would be if when you allocate set1, it happens to be the last object on the slab cache, in which case there's not necessarily going to be anything adjacent. But because we leak the address of set1 early on, we can actually compute which slot it is on the slab cache. And if it's the last one, we just try again, basically. Yeah. So this is nice because it will allow us to leak the address from VM Linux. And this is because the TTY structure has an ops function pointer table. And this structure has also been used previously in a couple public Linux kernel exploits, so it's fairly well known. But so this is what basically the modified scenario looks like, is we just have some TDY structure adjacent to set1 on the slab cache, and we've just modified the user data length to encapsulate both chunks, and then we can just read it all. And in this case, instead of like reading set1's ops, we read TDY struct's ops, and that gives us the .data address to bypass, like in VM Linux, which allows us to bypass KSLR. So the next phase is like, okay, we bypass KSLR. How do we actually get code execution out of this? So the idea is like, we need to put the KSLR adjusted pointers in memory somewhere. But fortunately, we just leaked the address of fake set1 while we were reading set1 itself. And because of fuse and setxadder, we basically can choose when we free the chunk, and we can just reallocate it. So basically, we can just free fake set1 on demand and replace it with a new fake set. But this time we know the address of where it's going to live. So we can put the KSLR adjusted pointers into fake set2. And so this case, because it's yet another new chunk that's replacing set2, I call it use after free 4. And then we're replacing fake set1 with fake set2, basically. And the idea is we can just now point the function pointer table of fake set2 back into itself at some offset inside the inline data, and that area can have the KSLR adjusted pointers. So yeah, basically we just free the setxadder chunk by unblocking fuse and letting the read complete. And then we just use fuse and setxadder again to replace fake set2 in the exact same slot on the slab cache. And then that basically lets us control the function pointer table. So now the idea is we're going to call one of these function pointers from this function pointer table, but it's fairly limited as far as like register control goes and stuff. Basically, half the functions you have RDI and R14 pointing back into fake set 2, and then the other half is RSI and R12. But because fake set 2 is completely controlled in memory, it's not too bad, because you can maybe find some gadget that is referencing interesting data at some offset from those registers and then using it, in an interesting way. And we just used the ROP gadget hunting tool RP. We didn't do anything fancy for that. I'm just grepping for the relevant registers. And so yeah, we ended up finding not so much a gadget, but an actual function, which is just basically responsible for unlinking something from a doubly linked list. And so again, I had said that RDI is one of the registers that points into fake set 2. So you can see RDI plus hex 60 will overlap with some of the fields, and it gets read into RAX. And then hex offset 68 gets read into RDX, and then it basically just writes RAX to RDX. So this immediately is like an 8-byte write primitive that we can use. And then, as usual with unlinking something from a doubly linked list, it will also try to write the other pointer back. So in this case, RDX will be written back into RAX, which is a potential problem because it will oops if RAX is actually like an arbitrary value. And so the question is, does the oops matter? And it does not, because on Ubuntu, they basically use this sysctl setting called panic on oops, and they set it to 0. And so basically, as long as like an oops happens in like a non-critical kernel path, the kernel just says, okay, just like pause or terminate that thread and then just keep going. But at that point, we've already triggered the first 8-byte write to a controlled address. So that's kind of all we need. Interestingly, like afterwards, I think fairly recently, Star Labs released a blog that they talk about using a similar function called list delete. I'm pretty sure it's almost identical. And they did something similar, but they actually could avoid the oops by abusing FizzMap, which I don't have time to get into. But it's a really cool technique, so worth reading about that as well. But we didn't need to worry about FizzMap at all because fortunately Ubuntu was the target and we just let it oops and there's a little stack trace in dmessage and that's it. So we don't really care, especially for something like Pwn to own. the question is, how do we invoke the gadget? So we chose to use this garbage collection initialization routine just because it was with the values that we overwrite in NFT set in order to use the gadget. It had the least constrained sort of code path to trigger. But basically you just need to initialize some expression that has this garbage collection flag associated with it, which there currently only seems to be one in the kernel called connection limit. And as long as like when you're initializing that expression, this flag is set, then it will just call GC init. And that's pretty much all you need to do. So probably, unsurprisingly, we targeted modprobe path just because it's like the path of least resistance, no pun intended. And it's super well documented, technique by now. And basically the kernel just has a writable string, and the string is basically used to run something responsible for handling module loading at runtime. So userland tries to trigger some functionality, and there's no module loaded, so it tries to execute this path as root. And so you can just overwrite it. So in this case, we are limited to 8 bytes, but we can just write like temp/x, and just we control temp x on the system, so we can run that as root. Obviously, like in real world scenarios, like outside of something like pwn to own, there's some limitations with like being able to write just a short string like this. For instance, temp might be mounted as non-executable. And then like if you're trying to exploit it from inside of a container, for instance, your /tempx is not going to be the same like path as what the whatever's running the module, like the mod probe path binary's temp path is going to be, because typically like they use overlay paths and there'll be like a GUID or something. So like you wouldn't control temp x in the actual the right context. So, but in our case we didn't care because we were just trying to do it for pwn to own, so it's enough. So basically that's what it looks like. Once we've crafted fake set 2, you can see that now the ops pointer points into the structure itself, which we can do again because we leaked the address of fake set 2 when we leaked the contents of set 1. And then we just have like the fake function pointer table where GC init points to the gadget, and we can see that the gadget will reference a couple members in fake set 2, field count and use, and then number of elements and another one. But fortunately for the code path to hit GC init, none of those members actually get referenced, so we just don't care. We can just put arbitrary data there. And that's basically enough to overwrite mod probe path. So just to go back from the very beginning, so there's basically 4 use after frees, I guess, that are getting triggered. The first one, we end up using the user key payload in order to leak the address of set 1 in memory. The second one, we end up also triggering the use after free of a dynamic set and replace the structure with a C group FS context, which lets us overwrite release agent. And then when we destroy the C group, it ends up freeing release agent, which allows us to free most of set 2. And then we can replace set 2 with fake set 1. And then that allows us to read set 1's, structure from memory, which allows us to bypass KSLR. And then finally, we replace fake set 1 with fake set 2 in order to execute the ROP gadget. And then, overwrite mod probe. And then all you have to do from user land is try to trigger some functionality that there's no module for. And then you basically get root. So, basically the way they patched this was a little bit different than we thought, because we thought maybe they would just modify the destroy routines to unbind, from the set. But they did something a little bit more robust, which is that they don't initialize the non-stateful expressions at all when you're creating the set. So basically they're never going to do the allocation or anything. So you basically avoid any case where you have desynchronization between initialization and destruction, which is good because well, good and bad, because it also fixed a separate bug that we had found also related to the desynchronization. And I think there is probably a lot more there. I wouldn't be surprised if, other people had found some of those. But we can see in the patch, basically when it's doing this expression initialization stuff, what it does first is it parses out the information about the expression into like a little structure without actually calling the initialization routine or allocating it. And then it checks the flag from the data it collected first. And then if it's non-stateful, it exits, and only afterwards will it actually try to allocate it if it's the right type. So, in conclusion, I guess, I think NF tables is probably going to have a lot more bugs. Like, I showed there's quite a few blogs about it already. I won't be surprised if there's more this year. And as far as like what made it easier, obviously like unprivileged namespaces are bad. So I guess people should disable them if they can. And which some distros do. This panic on oops thing seems dangerous. Everybody's been using Fuse server and setxadder ever since user fault FD got killed, so it seems still super powerful. And mod probe path is pretty common. I guess one of the things that's kind of interesting about exploiting this bug, aside from the fact that it was kind of limited in so far as what you could write to the free chunk, is a lot of exploits lately have been using this message structure in order to build like arbitrary read primitives and write primitives and stuff. But in this case we didn't have to use it, but actually in this case we couldn't use it anyways, because in Ubuntu 22.04, when they upgraded to 5.15, there was a change in the slab cache sort of layout. So message is now, I think, accounted. There's like some new accounting, like bucketing for slab caches. So you basically can't allocate the message structures to replace certain types of other objects you might want to use during use after free. So it's kind of interesting just that we didn't have to use it, because everybody likes to use it lately. And if you just spend enough time understanding the underlying code and stuff like Sam mentioned in his presentation, you can find typically ways to abuse, the place that you're already working on to find primitives and whatnot. So as far as like some mitigations go, like how to avoid these, there's some pretty obvious stuff. I think the thing that was surprising to me the most was probably that when we first had the idea of like freeing set bindings address or expression bindings address, I assumed that given that a slab cache is broken up into like objects of the same size, it would check whether or not you're freeing a misaligned address, because I don't think there's a legitimate reason why you would ever do that. Maybe there is, and I'm not aware. So if you know, tell me. But I feel like they could probably just prevent that in the future, which would at least make things a lot more annoying. And then there's other mitigations that are kind of coming out or been around for a while. JR Security has one called Auto Slab. And I think like last week or something, Google posted some information about some experimental mitigations that they're working on that are coming out of the KCTF challenges, which is for targeting like Kubernetes sandboxes and using kernel exploitation to break out. But the idea is like all slab caches will have like will be object specific. So if you allocate like the dynamic expression structures on some slab cache and then you free one, you can't replace that with a different, like some C group FS context structure. It will just prevent that entirely. And if you're familiar with stuff that people have been doing like in the last year or so with targeting like the buddy allocator, you might think, okay, well, even if I can't replace the object with a different type, maybe I can free the entire slab cache and replace it with a new slab cache after the fact, with totally different object types. And people have been doing that already lately. I think there's been 3 blog posts maybe in the last year. But I think AutoSlab has some functionality to avoid this, and Google's mitigations their proposal anyways seems to have some ideas about preventing this. So any memory that's ever been used for a slab cache of a specific object can't be used for a different type of slab cache after the fact. So that will be kind of interesting, but I don't know if that'll actually make it to mainline anytime soon, because there's lots of cool mitigations that exist that don't make it. Which leads me to like control flow integrity. So that's been around inside Android for a while already, but I haven't heard lately any like movement for getting that on x64, and that would at least prevent the ROP gadget execution stuff. And then other obvious stuff, you could set panic on oops to 1, which would at least prevent the gadget that we use, but there could be other gadgets and stuff. And I suspect in the real world it's pretty inconvenient, because if you just occasionally look at your D message output, you might notice things like Ubuntu semi-regularly will oops. And then if every time that took your box down, it might be kind of annoying. And then, yeah, so there is like a config option called config static user mode helper, which makes modprod path read-only. And I don't know why it's not used by default on Ubuntu and certain other kernels. If you know why it's not by default, I'd be curious, because I don't know a legitimate use case that people are regularly doing that warrants being able to update the path. I assume there's one, but I don't know what it is. And then, yeah, like some distros just don't allow unprivileged namespaces, which just removes this entire attack surface, which is, I guess, better than almost anything else. And then you could always get rid of userland Fuse server support and stuff. But there's a fair bit of stuff that relies on Fuse now, so it might be a little bit harder to do. Yeah, so that's basically it. We're going to release a blog with like a bunch more details and a few more diagrams and stuff. And this was a team effort. So like I said, it's a team of 3. Different parts we all worked on together. So it's Cedric and Alex and I did it together, and we are hiring. We're looking for a 4th person. So if you find this kind of stuff interesting and potentially want to do it with us, you can check out the link in the slides when I share them, or you can find me. Yep. And one last just random tidbit, which is not related to anything I just talked about, but so for the last like maybe 10 plus years, I have really bad repetitive strain injury. And so about 2 or 3 years ago, like I had to basically stop using my hands for using computers entirely and the mouse. And so I've been doing all of my research using a voice coding framework and an eye tracker machine for like tracking my eyes instead of using a mouse. And I use this free tool called Talon, which is amazing. And there's a lot of open source code surrounding it to help people that have these kind of disabilities or whatever use it and keep doing research. So I just wanted to give a shout out to that project, because otherwise I probably wouldn't be able to keep doing my job at all, and just say like, try to take care of your hands and your posture and stuff, because if you don't, 20 years later, it can catch up with you and it really, really sucks. Yep. So that's it. This should say questions, but
thank you very much, Aaron, for that talk. Please give me a round of applause. So we have a couple of questions up on the screen here, and just a reminder, if you are in the room and you'd like to ask any questions, you can use Slido for doing that. So we'll start off with the top one there. What does your process tooling for searching and enumerating new primitives look like? For example, is it predominantly automated via code QL, manual auditing, or a mix?
Yeah, I would say it's mostly manually auditing. Like a lot of it is first just trawling the existing tooling and blogs and stuff that exist, because a lot of the time, like, there might be some one-off scenario that someone already talked about, and at the time you weren't interested in what's in there. So a lot of it is just like actually reading stuff that is at least loosely related to the same topic, that's not exactly the same target, just to get some ideas. I personally mostly just look manually, like I try to understand, and I mean manually, like grepping for stuff or whatever. But Alex specifically has had good success using CodeQL for automating stuff. And in the case of like finding this C group C or FS context structure, it really worked well. So I think we'll probably start using it more. I had not used it before. So I think it will become a mix more afterwards. Yeah.
Awesome. Thank you very much. And second there, in your view, have Linux kernel vulnerabilities been increasingly hard to find over the years? If so, why do you think this trend exists, or does it not?
I would say not, but like, I mean, it's hard to say, like, so a long time ago, like say 15 years or whatever, you could just kind of grep the source code and just find bugs, like they just fall out of the sky. And so in that sense, it's easier. But now that there's good fuzzers, like if you look at the amount of bugs that something like syscaller can drop out, and if you look at the results of something like that, like Syzbot, which is Google's like fuzzing infrastructure that uses syscaller, there's tons and tons of bugs that are just not even triaged. And in the example of the one we did, it turns out it just closed as invalid, which clearly it was valid. And so in that sense, I think because of the, improvement in the ability of fuzzers to find more harder to find by hand bug, like manually find bugs like use after freeze, it's actually become easier. And I think it's just easier to augment fuzzers and stuff now than it used to be because there's such a good corpus of there's a whole community, in our industry that loves fuzzing, and they share tons of details about how to customize grammars and all this kind of stuff. So in that sense, it's become easier, I think. I would say that there's more. I remember like before, maybe it's just more attention now, less attention in the past. But I remember like times when maybe in a year you'd hear maybe like 2 or 3 cool Linux kernel bugs. But now I feel like every other week there's some potentially exploitable bug. So yeah, I think it's gotten easier. Hopefully that answers the question.
Yeah, thank you very much for the detailed answers. And thank you to those who have asked questions in the audience. Please join me again in thanking Aaron again.
Thank you.